because I think that period 6 will be interested also. We're going to be looking at problem number 38. And what we have in number 38 is a 3.6 kilogram ball. That's actually a very heavy ball. I'm not sure what kind of ball it would be. It would be something made out of metal. And a softball is actually much lighter than that.
Ball bearing?
What about a ball saw?
Ball bearing?
This is, 3.6 kilograms is going to be times 2.2, so that would be about 8 pounds, which is an 8-pound ball. Bowling ball, maybe a shot put, like a JV shot put, something like that.
Ball bearing?
And we're accelerating this ball at 7 meters per second squared by means of the tricep muscle. Now the triceps is
So it's like a weight, 8 pounds weight.
So you're throwing it like this.
yeah, so you're throwing it like that, and your triceps is pulling back, right? Okay. And so we have the whole thing can be visualized like this. And the 2.5 centimeters is the distance from the point of rotation in your elbow and there's going to be a force, we'll call that the force of the triceps, like so. And there's going to be, as a result of this, a force put onto the ball, just like so. Everybody with me?
Can you go over that one more time?
Sure. You have your elbow right here as a pivot point. And your triceps is now going to pull, and it doesn't pull right at the elbow, it pulls at a point just below the elbow, only 2.5 centimeters, or 1 inch below the elbow.
So why do you have the force going to the...
Because it is the triceps that is pulling. So if we're like this, here's my triceps, it's pulling like that. And what I do, in fact, everybody do this because it feels kind of strange. Put your elbow like this. Don't do anything with your left arm. Just use your right arm to pull back like that. And when you do, what happens to your forearm? When you pull like that, your forearm is compelled to rotate around the elbow. You feel that?
So how do you pull it?
Stick your left arm like so. Grab down here with your right and pull it like that.
I don't know.
Your turn on. Okay. Now pull backwards. See? You are compelled to rotate your arm forwards.
That's just not my own arm
So that's
moving.
just the hyperextend.
All right.
So
So-
our elbows want hyperextend?
No, it's not hyperextending. It's like normal extension. Hyperextending would be like going
Your
this way.
What's this then?
That would hurt.
Hermione Granger. Okay. So now here's the key thing. This is a classic example of a lever. And a lever is one of several simple machines that trades off force for distance. That's what machines do. If you look on the video from 6th period, we have another example of a different kind of machine, gears, actually sprockets and chains. And the trade-off there is between force and speed. Here, we're going to trade off force for distance. And I'll show you how it works. If I take the sum of torques around the point of rotation, then that sum of torques around the point of rotation has to equal I times alpha, right? Okay. And now let's consider all of the torques that are acting. First of all, we have the triceps force. Okay. And now here we have to be careful about this. What we're going to do is notice that the force, the FB right here, is the force that the hand is exerting on the ball. So the force that's actually being exerted on the arm is a reaction force that is equal but opposite to that. We'll call that FB. And we can figure out the value of FB really easily because FB is accelerating that ball. And so we can say that force is equal to the mass of the ball times the acceleration of the ball, or 3.6 kilograms times 7 meters per second squared. And 3.6 times 7 is going to be 25.2 kilogram meter per second squared, which is the same as newtons. And that is going to exert a negative torque on this thing here, having a tendency to rotate clockwise. So we have the force of the ball times 31 centimeters like so. And now if we assume, I think the problem allows us to assume,
Why do you write lever?
the problem allows us to assume that the I for the arm is negligible. Therefore, all of this has to add up to 0. Now here's what I want you to observe. If we call this distance little d, we call this distance big D, and what we see when we solve is that the force of the triceps times little d has to equal the force on the ball times big D. In other words, if I take ratios of forces, am I doing this right? Yep. That's exactly right. If I do ratios of forces, then I see that the force exerted by the triceps is going to be inversely related to the distance that it is from the point of rotation. In other words, the closer you are to the point of rotation, the harder you have to push. Now, why do I say that this is a trade-off? Well, because my triceps can pull really hard. It's a very strong muscle. And in fact, if we plug in the numbers here, we have a force of 25.2 newtons on the ball, and we have a ratio of 31 to 2.5, which is about 12 to 1, 12.4. And if I solve now for the force on the triceps, the force on the triceps is 315 newtons. That's a huge force, right? But even though I have to exert a huge force, the triceps only has to pull a very small distance. And in exchange, now this arm goes a very large distance like this, and it's able to accelerate the ball very quickly. Does that make sense to everybody? So this is an example of a lever. And the general picture of a lever is like this. You have some sort of fulcrum point. In this case, it's the elbow. And you have F1 and D1. And you have F2 and you have D2. And now, in order to be in balance, the torques have to be equal. So we can say that torque on this side equals torque on this side, or F1 D1 equals F2 D2. We call the ratio of D2 to D1 the mechanical advantage of the lever. So if D2 is twice as big as D1, then we have a mechanical advantage of 2. And what does that do for us? Well, D2 over D1 is the same as F1 over F2. So that means that F2 only has to push, if this is a 2 to 1, then F2 would only have to be half as big as F1 in order to balance it out. But when these two start swinging, the guy on this side has to go only half the distance that this guy has to go. So he uses half as much force for twice as much distance, or twice as much force for half the distance. He's trading off force for distance. Does that make sense to everybody? Now, what are some examples of mechanical advantage? I'll give you one. A screwdriver. How many of you have used a screwdriver before? All right? all, right? And what's the point of the screwdriver? The point of the screwdriver is you've got this little tiny nut, and you sit there and you try to hand tighten it. And when you try to hand tighten it, pretty soon you get to the point where you can't hand tighten it anymore. So then you grab the screwdriver and you start turning, and lo and behold, it turns more. Why does it do that?
So it's because it's smaller and or it's actually in it.
You're getting mechanical advantage. Let's take a look. This is the radius of the screwdriver, right? And this is the radius of the nut, and the forces that are being exerted on that, I said nut, on the bolt. The forces that are being exerted on the bolt are frictional forces on the edge, right? And so we have the torque on the little radius has to equal the torque on the big radius. Why? Because the screwdriver is a rigid object.
What if you have the, like, one force goes this way and goes this way when it's turning?
Right, but it's all going to cancel out. So if I compute the total force here and the total force here, then I can see that the mechanical advantage of my screwdriver is equal to the relative ratio of the handle size to the bolt size. So if I have a big fat handle, then that's going to give me a lot of mechanical advantage. It's going to make it really easy to turn. But the downside is that I'm going to have to turn a lot here just to get that bolt to turn a little bit down there.
Is that the same as gears? And it's like the big handle's like a big gear.
It's very similar to gears. And if you look at the other video, it'll explain about sprockets and gears, and you'll see a similar kind of a proportion right there. So there you go, simple machines. You guys have a great day.